Hey everyone, this is Dr. Walker. This is example v082 from Energy in Simple Harmonic Motion. Let's look at this example. It says that we have a block on a spring, is pulled a certain distance and then released. The subsequent oscillations are measured to have a period of 0.8 seconds. At what positions is the block's speed 1 meter per second? Notice that position is in parentheses. If we imagine a motion, the block is pulled at a distance of 20 centimeters. That's from the equilibrium position where x is equal to 0. So that means that this distance that is pulled, that's going to be the amplitude of the oscillation. It's never, if you pull it 20 centimeters, it's never going to get past that. Let's go ahead and write down our given. So A is 0.2 meters. And then the mass right here is 500 grams. So that is 0.5 kilograms if we divide by 1,000. And we have a period of 0.8 seconds. So when this block is released, it's going to start speeding up, right? It's going to have its maximum speed here at the equilibrium position. And then it's going to slow down and stop when it reaches this position here, which is also has the distance from equilibrium is also the amplitude. So there are two positions, one on either side of equilibrium, at which it will have this speed of 1 meter per second. How do we find it? Well, we're going to use conservation of energy. We learned that 1/2 Ka squared, which is the energy when the block is at the amplitude, at the maximum position on either side, that total energy is equal to the spring potential energy 1/2 Kx squared plus the kinetic energy 1/2 mv squared. So we're looking for the distance x. That's the position that it will have on either side, where it's going to have that certain v that we are given. So let's go ahead and solve for x. Let's simplify a little bit. We can cross out the 1/2 here. And since we're going to solve for x, we can go ahead and divide everything by k to get rid of 2 of the k's. So get rid of that k. And now we can solve for x. We're going to subtract this term over to the left side. So we have a squared minus this minus mv squared over k. That's going to equal x squared. So we're going to go ahead and take the square root of each side to get x by itself. So the thing is that we don't have k. So how are we going to find that? Think about what we're given. We're given the period. So this is going to be a 2-step process. From the period, what can we find? We can find the angular frequency. So we can go ahead and do this on the side. We know that the angular frequency is equal to 2 pi f, which is 2 pi over t, right? Because frequency is 1 over period. So if we do 2 pi divided by 0.8 seconds, we're going to get 7.85 radians per second. And now we know that omega is related to k because omega is equal to the square root of k over m. So that means that we can say omega squared is equal to k over m. So if we wanted, we could solve for k, right? Because we do have m and we do have omega. But I went ahead and just squared both sides because we have m over k here. So if omega squared is equal to k over m, we can just put omega squared here in the denominator. So we're going to have the square root of a squared minus v squared And then we're going to replace k over m here in the denominator by omega squared. But if you prefer to solve for k, you can definitely do that. And now we can plug in our values that we found. So the x is equal to 0.2 squared minus 1 squared over 7.85 squared. Remember, when you take the square root, you're supposed to put a plus or minus in the front. And that makes sense in this case, because we know that we're going to have this position on either side of the equilibrium position. So it's going to have a negative position and a positive position. Plug all the numbers in, we're going to get plus or minus 0.15 meters, or 15 centimeters if you want to put it back to centimeters. So this was an example of using conservation of energy, in this case to find position, but you could solve for any variable. The thing to understand is really that the total energy is 1/2 Ka squared. That allows you to find x or v or any of the other variables depending on what you are given.